Hello class, today we're going to go over Unit 8, Lesson number 6, and that's 8.6, Solving Logarithmic Equations. Okay, so we're going to go over a few strategies today about how to solve those with one variable algebraically. Just a little thing I want you to keep in mind at the side here. If we are solving for log, if we are solving for a variable with log, and x is in the argument, as you can see here, I just want you to remember, if you get to a point where there could be various answers for the x value, you have to remember that the argument of log is always greater than 0. Okay, so if mathematically when you calculate, maybe you get a plus or minus possible answer, remember that the final answer can only be the positive version, since the argument of log is always greater than 0. Okay, all right, so strategy part A. This is finding a common base between the two log expressions on either side. So what that means is if you have log of x to the base a equal to log of y to the base a, if you have two logs equal to each other and they have the same base, then the only way they can be equal to each other is if their arguments are equal. Okay, so that means x would equal y. All right, so let's look at these equations. We've got log x to the base 3 equals 4 log 3 to the base 3. So right away I'm noticing it's a scenario where I have a log expression on both sides, and they both have the base of 3. So I know I'm going to try to work with this strategy. The first thing I have to do, though, is you can't have any coefficients in front. So we have to rewrite this for its true argument. So we're going to bring the 4 back up as the exponent on the argument. Right, based on our log law, we can go back and forth. So on the right here, we're going to get log 3 to the 4, right, to the base 3. So now you're going to evaluate 3 to the 4, so that means the argument of this expression is really 81. So if you notice here, right, we have log x base 3, log 81 base 3. The only way that this equation can be true is if x equals 81. So the two arguments have to be equal to each other, right? So that means this has to be equal to this. Okay. So your final line would be x equals 81. All right, let's try again. We've got log of 3x minus 5 to the base 7 equals log 16 to the base 7. So again, this looks like this scenario right up here. All we have to do now, since it's the same base there, is now we just have to equate their arguments. So the argument here is in blue, 3x minus 5, and on the right side the argument is 16. So all you do is set them equal to each other, and then you're just solving a linear equation by isolation. So bring the 5 over, so it's 16 plus 5. We get 3x equals 21, divide both sides by 3, and we get that x equals 7. Good. Okay, and notice you always do this when you have two log expressions on either side of the equation. Okay. Option B is when converting to exponential form and then solving using common bases for exponentials is what's going to help you. In this scenario, because sometimes students get confused when they convert, you convert to exponential form when it's given to you in a form like this. So when they give you, for example, log x to the base a, and then say that it's equal to y. So that means, as you can see, that log is only on one side of the equation. Okay, so it involves us converting it to the form a to the y equals x. All right, so solve each log by converting to exponential form. So the first thing we're going to do is we're going to rewrite this as x to the negative 1/2 is equal to 6, right? Doing that wraparound method. Okay. So we get x to the negative 1/2 is equal to 6, okay, in purple. So then what you want to do is we have to think, how do we get rid of this exponent? Excuse me, how do we get rid of this exponent of negative 1/2? So a trick is that you always raise If you want to get rid of negative 1/2, then you have to raise it to its reciprocal. So the reciprocal of negative 1/2 is negative 2. So think about it. If you do negative 2 times negative 1 over 2, you're going to get positive 1, and that's what we want. We want x on its own. So this is going to be x to the 1 equals, and then whatever you do to one side, you have to do to the other. Okay? So you have to do 6 to the negative 2. So here, let me just draw. I'm going to do the exponential form so you can see how we got that. Okay. All right, so what does that give us? That will give us x to the 1, which equals, and then here, 6 to the negative 2, we can actually rewrite that using our exponent laws as 1 over 6 to the positive 2, right? Bring it down to the denominator. And so that leaves us with x equals 1 over 36. And that works here. So notice here, the x we were solving for was the base, okay, and the base always has to be positive and not equal to 0 or 1. So this number works, okay, so 1 over 36 works. All right, next one, we have log of 5x minus 2, so that's an argument, equals 3. So right away, notice when I see x in the argument, I'm just going to verify to myself, I know that the argument must be positive, so 5x minus 2 must be greater than 0. And if I were to isolate that, I would get that x must be greater than 2 over 5. Okay. And I know that the answers that I got up here also worked, so if I put in 81, that would be positive, and if I plugged in 7 into the argument here, I would get 21 minus 5, which would be a positive number, so that answer works too. All right, let's convert to exponential form. Now notice that there's no base number here, so that means that the imaginary base is 10, okay? So we're going to write this as 10 to the 3 equals 5x minus 2. So we know 10 to the 3 is 1,000 equals 5x minus 2. And now we are solving a linear equation. So we're going to bring the plus 2. So 5x equals 1,002. Divide out 5 from both sides, and we get that x is equal to 200.4. And that works because it is definitely greater than 2 over 5. All right, log of 0.04 to the base x equals negative 2. Okay. So let's convert. So we get x to the negative 2 equals 0.04. Okay. All right, so when we do this, okay, we have to say to ourselves, okay, we have to get rid of the negative 2. Okay, so you can do two things. You can at first raise it to the negative 1 to get rid of that, and then obviously you can square root both sides. So when doing this, we're going to take the reciprocal of it, so we're going to raise it to negative 1 over 2, because negative 1 over 2 times negative 2 would give me x to the 1. Okay, so next, sorry, just to put in here, because we're basically taking a square root of a value, you should put the plus or minus symbol in here, okay, because we're square rooting both sides, and then whenever we do that, that means we do plus or minus. Okay. All right, so that leaves us with x to the 1 equals, the negative just means that you're bringing it down to the denominator, so 1 over, brackets here, 0.04 to the 1/2. Okay, again, we'll put that plus or minus in there. Okay. So that leaves us with 1 over plus or minus 0.2. Okay. And that leaves us with plus or minus 5. Now, because x here is a base, okay, so let me write this in a different color. So x is a base, so the base, okay, must be greater than 0, okay, and not equal to 1. Okay. So that means, according to that restriction, that the base cannot be -5. So that means I have to go with the positive answer. So therefore, x equals +5 only. Okay. So even though mathematically you get plus or minus 5, 5 is the only thing that can be a base value for log. Okay. All right, and the second way we can go about solving may involve, the third way, this will involve us simplifying using laws of logs. So that's just remembering that log m times n to the base a is equal to log m to the base a plus log n to the base a. Log m divided by n to the base a is the same thing as log m minus log n. And log m to the n is equivalent to n times log m to the base a. All right, so let's see what happens here. It says solve each log by writing as a single logarithm. So when they say write as a single log, that is a huge hint about your log laws here. Okay, so at some point you are going to have to go from this to this, from right to left, and from right to left again. Okay. So as we go through, we have log 4x plus log 5 minus log 2, and they're all to the base 3. So that means I can use my log laws to combine this side as a single logarithm. Okay. I do notice that x is in the argument here. So I know that 4x must be greater than 0, so therefore x must be greater than 0. Okay. All right, because these two are being added, I can take their arguments and multiply them. Okay. And then since after that I'm taking that and subtracting log of 2, that means I can take their product and divide it by 2 according to these two rules. So I can write this as log 4x times 5 divided by 2, all to the base 3 equals, and then that 4 remains. Okay. So let's simplify. That's log of 20x divided by 2 to the base 3. So log of 10x to the base 3 equals 4. All right, so now we're in a similar scenario as we were in part B. So now we're going to convert to exponential form. Okay, so now we're going to do the wraparound method. Okay, so we're going to do 3 to the 4 is equal to, and then the argument. Okay, so 3 to the 4 equals 10x. 3 to the 4 is 81. So 81 equals 10x, and now divide 10 from both sides. So x is equal to 8.1. And I just make sure my answer works up here. Yes, 8.1 is greater than 0. All right, part B. We've got log of x minus 2 to the base 3 plus log of x to the base 3 equals 1. So we're going to have to combine this left side. They have the same base. Before we begin, I'm just telling myself here that if x minus 2 must be greater than 0, then that means x must be greater than 2. And x is on its own here, so x must be greater than 0. Okay, so some restrictions to keep in mind. So I advise you to always do your restrictions first. Okay, because we're adding these two, we can multiply them. So we're going to get log of x minus 2 times x all to the base 3 equals 1. Now we're going to distribute. Okay, so you're going to do your FOIL. So we get log of x squared minus 2x equals, or to the base 3 equals 1. All right, now we're going to do our wraparound method. Okay, so we're going to go 3 to the 1 is equal to x squared minus 2x. All right, so as you can see, we now have, in the other kind of examples up here, we were left with linear functions. Now we're left with a quadratic. We have x squared minus 2x and then equals 3 to the 1. So how do we solve quadratic equations? remember, you can't just isolate x because it often appears more than once, as you can see here. So that means you have to bring all terms to one side of the equation and set one side equal to 0. Okay? The only time you don't do that is when it's linear, because you can just isolate right away. So we get 0 equals x squared minus 2x minus 3. Okay, and then this is a simple trinomial. So we're going to look for two numbers that multiply to -3 and add to -2. So it's a -2 there, and that's hard to see. Let's fix that. Okay, and those numbers are -3 and 1. Because it is a simple trinomial, right, you can plug it in right into the brackets. So we get 0 equals x minus 3 times x plus 1. Okay. All right, how do we find our roots? We set each factor equal to 0 and solve. So this produces a root of x equals 3, and this produces a root of x equals -1. Now, this is where you're going to have to really be paying attention. So I'm calling x equals -1 as inadmissible. Okay, because it does not meet the domain requirements here. Okay, so x has to be greater than 2, x has to be greater than 0. So out of these two, x greater than 2 takes over. Okay, all right. If you're doing x greater than something, then the one that takes over is the largest number. Okay, so this definitely doesn't fit in that requirement. Okay, so let's just write here. Since x must be greater than 2, okay, which means therefore that the final answer, the solution is that x is equal to 3. Okay, so this is the only answer that works. All right, let's try again. We have log x plus log x squared equals 12. For both of these, the restriction is x must be greater than 0. So it's the same thing. So that's going to be the main one. They're being added with the same imaginary base of 10, so we're going to multiply their arguments. So log x times x squared to the base 10 equals 12. So we get log of x cubed. Okay. Put this in here. So we get log of x cubed to the imaginary base 10 equals 12. And now we are going to convert to exponential form. Okay. So we do our wraparound method. So there's an imaginary 10 here. Okay. So 10 to the 12 is equal to x cubed. Okay. All right, so we get 10 to the 12 is equal to x cubed. So over here, we need to get rid of the x cubed, so we have to take the cube root of both sides, right? Or the same thing as raising it to the 1/3. Okay, it means the exact same thing. Whatever you do to one side, you do to the other. So again, our goal is to get the exponent of 1. So if we do the third root of 10 to the 12, what does that actually do? So mathematically, this is taking 10 to the 12 and raising it to the 1/3. The operation between a power and a power is multiplication. So what is 12 times 1/3? Okay, that's going to give us 10 to the 4. Okay, and we know that 10 to the 4 is equal to 10,000. Okay, so the 4 means it's going to be 4 zeros. And then I look back up and my restriction was that x had to be greater than 0, so this works. All right, let's turn over. Let's do a few more. Again, here we have that the argument is x plus 3. So you ask yourself, okay, if x plus 3 must be greater than 0, when I isolate for x, what is going to happen? And what's going to happen is that you're going to get x must be greater than -3. Here we have an argument of x minus 3. So x minus 3 must be greater than 0. Okay. So when we isolate for x, that means x must be greater than +3. So because we're doing a greater than scenario, you want to take the larger of the two numbers. So 3 is larger, so this one becomes what you go, kind of what you base your domain off of. The x must be greater than 3. Alright, so we have a common base of 2, so let's multiply their arguments and write as a single term. Okay, so log of x plus 3 times x minus 3, all to the base 2 minus 4. So we're going to distribute. We can see that those are the factors of a difference of squares. So we know when we distribute FOIL and collect like terms, we're going to get an argument of x squared minus 9. And at this point, we are going to convert to exponential. So we're going to go from 2 to the 4 equals the argument. Okay, so 2 to the 4 equals x squared minus 9. 2 to the 4 is equal to 16. Okay. Now this is a unique case for a quadratic. I know with quadratics or other polynomials of degree 2 or higher, we're always used to bringing all the terms to one side, setting one side equal to 0 and factoring. The only cases where you can actually just isolate for x in polynomials of degree 2 or higher is when the variable appears only once in the equation. So as you can see here, this is a quadratic because of the degree 2. However, it only has constants with it. So what happens is we can collect the 16 and then bring the negative 9 over and collect those two together. We can do that because x appears once. The problem occurs is when you have, for example, an x squared term and then another x term. That means you can't isolate. So in this case here, we can bring the negative 9 over, so 16 plus 9. So we can get that 25, okay, is equal to x squared. Of course, we take the square root of both sides, and you have to consider the plus or minus. So we get that x is equal to plus or minus 5. So again, we have to go back up here, and it says that x must be greater than 3. Okay. So that means x minus 5, x equals minus 5 is inadmissible. Okay, and that's because x must be greater than 3. So the solution to this is just positive 5. So be careful here, because sometimes when students solve for an x value, the minute that they see, for example, the minute that they see a positive number, so say you got an answer of 1, they immediately think that 1 is the answer because it's positive. But as you can see up here, this restriction here was x greater than 3. So if you had gotten an x value of 1, students are misleadingly so will say, okay, 1's a valid answer. But if you were to plug 1 into the argument here, you would get 1 minus 3, and that would give an argument of negative 2. Okay, so then that wouldn't work. Okay, so always be careful there. Okay, and let's try another. This one's x minus 1, so the restriction will be that x must be greater than 1. X minus 2, so x must be greater than 2. X plus 6, so x must be greater than negative 6. So since we're doing a greater than scenario, we're going to take the largest number, which is 2. So this is going to be our domain. Alright, so we're adding these two first and then subtracting this. So that means these two arguments can be multiplied, and then those two multiplied can be divided by x plus 6 as a single log. Okay, so we have log of x minus 1 times x minus 2 divided by x plus 6, all to the base 5 equals 0. Alright, so in this case here, you're going to see why that instead of you can distribute the top part now, if you'd like, or you can go to the exponential form right away. It doesn't matter, you're going to kind of get to the same place either way. So we're going to do 5 to the 0 is equal to the argument. So 5 to the 0 equals here. 5 to the 0 is equal to 1. Okay. So what's nice about this case here is that we can just immediately cross multiply. Right? So we have 1 equal to and then a rational expression here. So 1 times x plus 6 is x plus 6, and then 1 times our two factors here are just the two factors. All right, now we can expand. So let's use FOIL to expand x minus 1 and x minus 2. And collect like terms, we're going to get x squared minus 3x plus 2 equals x plus 6. So this is a polynomial of degree 2, and it does have x values obtained there, so we are going to have to bring all terms to one side, set one side equal to 0. Okay. So I brought these two terms over and made them both negative. So that leaves us with 0 equals x squared minus 4x minus 4. So we go to the side, what two numbers multiply to negative 4 and add to negative 4? There are no two numbers that we can come up with to do that. Okay. So in that case, we are going to have to use quadratic formula. Okay. So we have a value of 1, a b value of negative 4, and a c value of negative 4. All right, so let's plug it into our quadratic formula. So we're going to get negative 4 plus or minus negative 4 squared minus 4 times 1 times negative 4 divided by 2 times 1. So we get left with 4 plus or minus root 32 divided by 2. So now we have to do our two cases. Okay. When you enter both into your calculator, the first answer you should get is approximately 4.8. And the second answer you get should be negative 0.8. So we go back up, we remind ourselves that x must be greater than 2, so therefore we classify this guy as inadmissible. Okay. X must be greater than 2. Okay. Alright, so that means the only solution is the 4.8. So x is approximately 4.8. Alright, I hope everyone's kind of enjoying it so far. You can see the process is super repetitive. So basically when you have, when you're working with all these strategies, you either, if you have two logs on both sides with the same base, you want to write them as single expressions and then equate their arguments. If you have a log on one side and a number on the other, then you want to convert to exponential form. And then if you have multiple logs on one side and a number on the other, then you typically want to write the one side as a single log expression and then move forward with the converting to exponential form. Okay. And just a word problem to finish off to see kind of how all of this applies. The Richter scale is used to compare the intensities of earthquakes. The Richter scale magnitude R of an earthquake is determined using R equals log of A divided by T plus B. So A is the amplitude of the vertical ground motion in microns. T is the period of the seismic waves in seconds. And B is the factor that accounts for the weakening of the seismic waves. An earthquake measured 5.5 on the Richter scale and a period of the seismic wave was 1.8 seconds. If B equals 3.2, what was the amplitude A of the vertical ground motion? So they gave us a bunch of pieces of this formula and we have to solve for little a. Okay. All right, so what are our values? So R is the Richter scale magnitude, so that's 5.5. They gave us here. A is what we're looking for. Okay. T is the period of the wave in seconds, so that's 1.8. And they said B is equal to 3.2. Okay, so let's plug that into our formula. Okay. So 5.5 equals log of A divided by 1.8 plus 3.2. So now we want to isolate this log term because we're trying to get to A. So to isolate A, we first have to isolate what the expression is part of, which is the log. So we're going to bring 3.2 to the other side. So 5.5 minus 3.2 will give us 2.3. And what scenario have we got ourselves into now? So this is a scenario where we're going to have to convert to the exponential form. Okay, so remember that means that there's an imaginary 10 here. Okay, so we're going to do 10 to the 2.3 is equal to the argument. Okay. All right, once you get here, you can cross multiply. Okay, so when we cross multiply, all right, put that over 1, we're going to do 1.8 times 10 to the 2.3, and then that's going to be equal to 8 times 1. All right, so we're going to enter that into our calculators, 1.8 times 10 to the 2.3, and approximately to 2 decimal places, you should get 359.15 microns. Okay. So this is just a symbol here called mu. It's kind of got a tail on U at the front instead of at the back. And that means our answer is the amplitude of the earthquake is 359.15 microns. All right, I hope everyone enjoyed the lesson. Lots of practice with this and it'll become very second nature to you. Good luck with the homework questions and let me know if you need any clarifications with things. All right, good luck.